for the next lesson, we will be using this formula. E cell equals E cat minus E anode. Using this equation, this electrochemical cell. So on the left side, again, we have zinc giving away 2 electrons, and the copper plus 2 takes the electron. So I wrote down the same equations here because that is too crowded, so you can see what's happening or how we use the equation. So here it is again, the zinc gives away the 2 electrons as it moves this way, and it goes to copper. We're going to figure out the voltage in that. Okay, so this is again the anode because the electrons go from A to C, and this is the cathode. Okay, so we're going to try to find the voltage using this formula. Okay, what is the cell potential of the cathode? So this is the cathode. All you have to do is look this up on the chart. So we go to the standard reduction table chart, we look for copper, and it is 0.34 volts. So it wants the electrons that much. Okay, so 0.34 volts. So this is 0.34 volts. So I'm going to plug that into the formula. The potential of the cathode is 0.34 volts. Now the formula says minus. Okay. I'm going to now do the potential of the anode. This is the anode right here. I'm going to look this up on the chart. Zinc to zinc plus 2. And here it is. I circled it down here. As you notice, it is going the wrong way. It needs to go backwards. It needs to be oxidized to give away the electrons. So it needs to go this way. So what the formula does is it includes a negative sign in front of this number, showing that it went the opposite way. Okay, so remember the cell potential is negative 0.76, right? So I'm going to go here. It is negative 0.76 volts. This negative right here is this negative right here. We'll flip the sign of this voltage. So when you add them together, you're going to get the potential of this whole electrochemical cell, which is 1.1 volts. Okay, so to review, the formula is to get the cell potential of 2 beakers or 2 reactions. 1, 2, you take the cell potential of the cathode, 0.34, minus the cell potential of the anode, negative 0.76. These 2 negatives become positive, and you get the voltage of that electrochemical cell. Okay, one thing about this voltage, the cell potential is based on the potential energy per unit charge, which means it's a ratio. Therefore, it is an intrinsic property. So what does that mean? So you understand density, right? Density is the mass per unit volume. If you double the mass, let's say the density is 1 gram per 1 milliliter. Okay, the density is 1 gram per milliliter. If you double the mass, you're going to get 2 grams, but you're also going to get 2 milliliters. So the density is still 2 divided by 2, 1 gram per milliliter. So the density does not change. That's what intrinsic means. Okay, it does not change if you change the amount. The same thing with cell potential. The voltage does not change because this is the amount of energy you get for a certain number of electrons passing through, or that number of charge, 1 coulomb. Okay? So what I'm saying is if you double the reaction, do not double the voltage. So if you look at these standard reduction tables, if you see this becoming 2, 2, 2, do not double this number. This is a ratio. Okay, so keep it just like that, 0.77. Okay, so in this chart, you can obviously see that as the farther apart they are from the table, the more potential you're going to get, because this is going to be plus 0.34 cathode minus the anode, right? So, and then you're going to become more positive, a big positive number. So if you look at this chart, the one that would give you highest voltage is a reaction between F2 and lithium solid, because they're farther apart. So this will become negative 3.05. You have to flip this equation. And 2.87, that's a lot of energy. That's about 6 volts. That's the most you can get out of this chart. Okay, let's do an example. It says for the zinc-copper voltaic cell shown in figure 20.5, we have this reaction right here. Okay, so you have zinc. I'm going to break this down so I can understand it myself. Zinc is becoming zinc plus 2. So what's happening to zinc? It is giving away 2 electrons. You can see that, right? Copper plus 2 is becoming copper, 0. So this is gaining 2 electrons. Okay, so zinc is becoming oxidized. What about copper? It's getting electrons, so it's going to get reduced. Okay, so go ahead and tell me which one's the anode and which one's the cathode. Okay, that's right. Remember, this is the anode, and there are 2 ways to remember it. O and A are both vowels. And also, the electron is coming from the anode. It's giving away the electron, and the copper is taking it. So this must be the cathode. Okay? Given that the standard reduction potential of zinc 2Zn is negative 0.76, so the reduction potential of this, as you see in the chart, is negative 0.76. That's what it's saying. And reduction potential, meaning it's really written backwards on the chart. Okay, you have to remember that. Calculate this E potential for the reduction of copper plus 2. So they want you to know this one. This will be your X. So they're looking for this potential for copper to accept the electrons. So they also gave you this E naught of the cell. Okay, so the formula is E cell is equal to E cathode minus E anode. Okay, the way I memorize this is cats are better than ants. Cats and ants. Okay, so the cathode standard reduction potential is negative 0.76. Oh no, cathode is X. And here's the minus sign. This is this minus sign. We'll flip this because I flipped that equation. Negative 0.76. And then this is a 1.1 volt. Okay, so X will be, if you solve for X, you're going to get 0.34 volts. So X equals 0.34 volts. So that is the standard reduction potential for copper. Copper plus 2, taking in 2 electrons to become copper. And as you can see, if you look at the chart, it is 0.34 right there. So you just solve for it.